So we're moving into part 2 of the course notebooks. If you're reading the course, if you're keeping up with the readings in the course notebooks. All right. So we're going to start talking about classes and how you create classes. But before we get there, we need to talk about some fundamental terms to make sure that everybody understands or has a clear understanding of what of the terms that we use to describe a Java program. So first of all, there's something called a type. We've talked about this before. A type is just a set of values and the operations that can be performed with those values. So for example, an int is for an int. So what are the set of values for an int? Well, it's any one of these 32-bit signed integer values between integer min value and integer max value. So those are the possible values you can have. Now, what are the operations that you can perform with an int? Well, there's all this arithmetic stuff and comparisons and lots of other things that you can do. Well, not so many other things. Essentially arithmetic that you can do with ints. Right. A string. So what are its set of values? Well, a string is any sequence of 0 or more Unicode characters. What can you do with a string? You can check if two strings are equal. It has a whole bunch of methods. And it has some operators, so like equals equals and not equals that mean very specific things. And then finally, there's a list. So what does a list? What are the set of values that a list can take on? Well, a list is any sequence of 0 or more elements of the same type. What operations can you do with the list? Well, there's equals, get, set, sublist, and so on and so on and so forth. So when you create a class, the operations that can be performed, those are the methods that you define in your class. What are the set of values? Well, the set of values are represented by the information that's stored in an object. Right? And so we'll see how that's done shortly. So you know what the primitive types are in Java, right? You know that there are reference types in Java, right? So anything that's not primitive is reference, right? So arrays are reference types. Even arrays of primitive values are considered reference types, right? And then any class is a reference type. And similarly, any interface is also a reference type. So string, that's a class. Array list is a class. Those are both reference types. List is an interface, but it's considered a reference type in Java. Okay, so what's a class? So a class is just an implementation of a reference type. So in other words, it's a way to define your own reference type. So in Java, a class is always a type. Not all types are classes. Examples of classes, well, there's string and array list, right? And basically any class that you create on your own becomes a reference type. All right, so what is an object? Now, an object is just an instance of a class, right? So it's similar to how 5 is an instance of an int, right? Or 3.2 is an instance of a little d double. When you make an object, you're creating an instance of your class. And the way that the object is created is that you take the class, and the class is used as a blueprint to make the object. So in other words, whatever is defined in the class becomes part of each object. Or you can think of it as being, you can think of whatever is defined. So whatever features are in a class, you can think of that. You can think of objects as having all of those features. So if I make a new array list, that creates an object, right, using the array list class. Right? So you have an array list object that is made using that class. Now, what's a reference? So a reference is an identifier that can be used to find a particular object. The other way you can think about this is it's the identity of an object. So in other words, where can we find that object in memory? And in fact, in many Java implementations, a reference is just a memory address. So for this class, you can think of a reference as just being a pointer to an object. except you can't do anything with a reference that you can't do anything with a reference except use the object. Whereas in C, you can do lots of stuff with the pointer. Okay, do you need a class instance to use its methods, or can you call these methods using the general class name? So that's a good question. In Java, there are two different kinds of methods. Broadly speaking, there are two different kinds of methods. There's a static method, which are the methods that we've been using mostly so far. So static methods, you always use using the class name. Then there are what are called, then there are just regular methods, or sometimes we'll call them non-static methods to distinguish them from static methods. But most methods in Java are non-static. So normally when you say method, you mean a non-static method. So with a non-static method, you need an object to call the method. Static methods use the class, don't need an object. A non-static method, you always need an object. You cannot use the class to call a non-static method. And you'll see why that's the case shortly. Right, so reference is it's just an identifier that you can use to find an object. In other words, it's fine for this course to think of a reference as being the memory address of an object. I think it's in most Java implementations that's the case, but it's not. The language specification does not say that they have to be, a reference has to be a memory address. So it is possible to do in other ways. But somehow you need to, when someone uses a variable, you need some way to figure out what object that variable refers to. And that's what a reference is. We know that any variable whose type is not primitive stores a reference. So in this case here, T, because its type is not a primitive type, T is storing the reference to an array list in memory. So for our purposes, you can think of thinking as T stores the memory address of this array of that array list object. Right. So if you give T a new value, that means that T is referring to a different list object. Okay. Now there's this thing called a memory diagram that might be useful for understanding the differences between primitive and reference types. So if you think of a reference as being the address, the memory address of an object, then a memory diagram is just a picture of memory. It's not an accurate picture of memory. So the way memory actually works on a computer, well, not on a computer, when you're in when you're running a program, is actually quite complicated. But we can use a simple or a very naive picture of memory in the following way. So you can think of memory in a computer as just being a table, right? So it's a basic. Well, here it's showing with 3 columns, but you can think of memory as just being a big array, right? So that's probably the easiest way to think about it, right? So here, that's a picture of my memory in this column here, right? So it's just an array. I can store one thing in each of these boxes, right? So I'm allowed to store exactly one value. How do I get to this box? Well, that box has an address, right? So if you think of this as an array, then this is just the index of the array. Addresses are unique. Every box has a unique address. So here, someone's unmuted. I'm just going to mute them. Okay. So every box has its own unique address, right? So that's box 98, that's box 99, and so on and so on and so forth, right? And then if you have a variable, we're going to stick the variable name out in this in the first column here. Okay. So for example, here I've got a double variable x, and its value is -1, right? So in the first column, somewhere, it doesn't matter where you put this variable, right? So for our purposes, you can stick it wherever you want, as long as there's an empty box to store it, to store the value in, right? So in other words, you can't put 2 things in the same box, and you cannot overwrite an existing variable. That's right. So if there was something here, sorry, there's an x here, so I cannot put a y here, for example, right? So I can't nuke a variable in our picture here. So somewhere there's something called x, right? X happens to be at the address 100, but this is a primitive type, right? So what does a primitive type variable store? Well, it stores the value of the primitive, I guess, object. It's not really an object, right? It's the value of the primitive instance, right? So in this case, x stores the value -1, right? So the value -1 really is sitting here in memory. Now, if I make a list, variable t, so there's my list variable t, is living at address 101. Again, you can put it wherever you want, right? It doesn't matter. And it refers to an array list object, right? So what value sits here? It's not the array list object, right? So in other words, there's not some object here that's got a bunch of memory associated with an array list. Instead, it's the address of that object. So the way I write that is some number followed by an A, right? Where the A indicates that it's an address and not a primitive value, right? I need some way to distinguish addresses because if it was just 700, that would look like an int, right? So I'm going to write 700A to indicate that's an address. And now when you go looking in memory at address 700, there's this array list object. Anything belonging to the array list object, so any memory associated with the object, would be sitting here, for example, right? So at line 701, there's some variable associated. There's some variable that this object uses to store stuff, right? And that might go on for some time, right? So at 702, there might be something, and 703, there might be something, and so on and so on and so forth. So references store memory addresses. Primitive types store values, right? Or store the value of the primitive instance. Okay. So now that we have the basic under the hood, in what way is memory more complicated than a simple table? Under the hood, in which way is so it's a lot more complicated. So where these values are stored in memory are probably different. And that's just the first difference. So when you make a method or a function in C, for example, right, then any local variable that's in the function gets allocated in a certain part of memory. Anything that you allocate with new, so anything that's dynamically allocated, that gets allocated in a different part of memory. And those two different parts of memory have different characteristics. So the local variables, those sit in memory that's much faster than the dynamically allocated memory. And that's just how the C runtime works. Once you then the C runtime interacts with the operating system. So how the operating system manages memory is a whole other story. And then how your hardware organizes memory is another story yet. So it turns out on a modern computer, it's extremely complicated how all of this works. You would need to take many, many, many courses, at least 3 or 4, to get a decent. Well, let's see. Even so, for example, if you took the 3rd year operating systems course in computing science, you would still only have a very superficial understanding of how memory works on a modern computer. So it's actually very complicated. So this picture here in particular is extremely naive, but it's sufficient for our purposes. Okay, so we now have I've now told you what all the basic terminology means. So now I'm going to describe how object-oriented programming works. So procedural programming is what you would have done in C. So basically, in a procedural program, you decompose your program into functions, right? And the functions get passed data to operate on. So in other words, your functions have inputs, data that the functions operate on. If you have global variables, then the functions can also access that information. And then the functions can return values. So they can return values back to the caller. And basically, a C program is composed of a bunch of functions, right? Where functions can call other functions. But no function owns any information, right? Information passes between the different functions. Except for the main function. I guess in a C program, the main function would be the place where you might store some information. In object-oriented programming, the decomposition is different. So you decompose programs into objects. The objects can interact with one another by calling methods on one another. And the objects are the things that contain the data. So objects contain data, they can operate on their own data, and they can ask other objects to operate on data. So on the level of just organization, right, that's different from a procedural program. There are four main elements in what are called the object model. So those elements are abstraction, encapsulation, modularity, and hierarchy. The hierarchy we're going to talk about later, but the first three items I can introduce now. So the first item is abstraction. And so this is a quote taken out of one of the main introductory textbooks in object-oriented programming. So it's a book called Object-Oriented Analysis and Design with Applications. Pretty famous book it's a pretty famous book in object-oriented programming. So the quote here is that abstraction is one of the fundamental ways that we humans cope with complexity. And abstraction denotes the essential characteristics of an object that distinguish it from all other kinds of objects. Right? And so that part in red, right, is suggesting that you can make different objects that can do different things. Right? So, for example, an object that's a list is different than an object that's a string, right? So in other words, we don't have just one class called object that does everything. And thus provide crisply defined conceptual boundaries relative to the perspective of the viewer, which is interesting. So I'll explain that in a moment. You Google the term abstraction, you might run across the Wikipedia article for it. Right? Actually read it. Oh, now I've lost it. All right. No, that's not it. Where'd it go? Here we go. Okay, Wikipedia tells you that abstraction involves the facility to define objects and represent abstract actors that can perform work, report on and change their state, and communicate with other objects in the system. Right? So perform work, they have methods. Right? Report on and change their state. That means they have data. Right? Communicate with other objects in the system. That means an object can call a method belonging to another object. Right? So I guess we'll leave it at that for now. You can continue reading that if you want. There's also a notebook that describes this. There's this other term here, though, this other part of the definition, relative to the perspective of the viewer. So in an object-oriented program, imagine that you decide to create, you are writing some program and you decide you want to create a class called car, right? So you want to make a class that represents an automobile. Now, what you put into that class depends on what that class is going to be used for, right? So in other words, whatever the user of the class wants to use the class for, that's what you're going to put into the class, right? So for example, you're making a car class because you're trying to create a website that sells used cars. Right? So you want to create a car class so that you can represent the information that a buyer of a car would be interested in. Right. So what information would you put in the class? You'd put things in like the make of the car, right? The model of the car, the year that it was made in, You might do things like mileage, right? So how many kilometers are on the car, and so on and so on and so forth, right? So that would be one way to define a car, right? Now, if you're making a car for a video game, it's completely different, right? So you're making some car for, say, Mario Kart or something like that, right? Then your idea of what's a car is completely different than what your idea of is a car for someone who's trying to sell one, right? Who's trying to sell a real world car. So if you're making a video game car, you might have things like, what is its top speed? What does it look like? How fast does it accelerate? And things like that. But what you wouldn't do is you wouldn't make one car class that has everything in it, right? So you wouldn't make a car class that could be used to sell cars or could be used in a video game, right? Right. In other words, you look for the essential characteristics that you need, right? So that's the idea of abstraction. Notice here that the first part is also interesting. So it's one of the fundamental ways that we humans deal with complexity, right? So abstraction is everywhere in the real world, right? So for example, I think everybody here who's listening knows how to use a cell phone, right? So we know that if you want to make a call with a cell phone, there's some button that you press that gives you a dial pad, and then you dial a number, and away you go, right? I'm just about 100% sure that no one on this call actually knows how the cell phone actually makes the call, right? So when you dial the number, what sequence of events actually happen in order for the call to be connected? I have no idea, right? And I don't think anybody else here has any idea either. And yet everybody here can use the cell phone to make a call, right? So we can say that the cell phone, the physical device, right, gives you an interface to make a call that anybody can use, but it hides all of the difficult stuff behind the interface. And that's the idea in object-oriented programming as well. You can make a class that can do all sorts of stuff. So we can make a list class. It has all sorts of capabilities, right? It has a bunch of methods that are easy to call, right? So it's easy to use a list object. But as the user of a list object, we might not have any idea of how it actually works underneath the hood. So that is abstraction. Right? Right. Now, there's another term that's also important. So there's a term called encapsulation that's used to implement an abstraction. Right? So encapsulation is the process of compartmentalizing the elements of an abstraction that constitute its structure and behavior. Right? Encapsulation serves to separate the contractual interface of abstraction and its implementation. Okay, so what does he mean by this? So he means when you decide that you need to create a class, right, going to compartmentalize that class into one place, or maybe several. But we're going to have one place where you can access the class, right? So if I make a car class, or if I want the idea of a car, I'm going to make a car class, right? And I'm going to put all of the details of the car class into the class, right? So I'm going to compartmentalize it. I'm going to put it somewhere, and then I'm going to separate the contractual interface of the abstraction and its implementation. So in other words, I'm going to provide a bunch of methods so that you can use the car class. Okay. But you don't need, the user of the class doesn't have to reach into the object and fiddle with the information in order to get something to happen. Right? So in other words, again, imagine you're making a car for a video game, right? To cause the car to go faster, you might have a method called accelerate, right? And you just call the method accelerate, right? What you don't have to do as user of the class is that you don't have to reach into the car object and then adjust the speed yourself in some way, right? So you're going to provide methods, right, that operate on the data that's the the object has, right? Okay, and finally, there's the third term, which is called modularity. So modularity is the act of partitioning a program into individual components. So you can kind of guess that one way that you provide modularity in an object-oriented programming language like Java is to create classes. So I'm going to separate all of the interesting stuff in my program into individual classes. Right? But that's not the only way that you can partition a program in Java. Right? So in Java, you have things called packages, where you can group together related classes. And then you have things called modules, where you can separate individual packages and hide them from one another. Now, why do you want to partition a program? In other words, why do I want to split everything up into classes and packages, right? So the answer is that you don't have to. It's entirely possible to write a Java program that exists in a single class, but trying to maintain such a program or trying to extend such a program becomes extremely difficult. It also becomes very hard to understand. So imagine you take a very complicated piece of software like PowerPoint, right? You can imagine PowerPoint is probably made up of hundreds, if not thousands, of different classes. Right? Now imagine instead of having it split up into 100 or thousands of classes, everything was in one giant class. Right? Trying to understand such a program becomes extremely difficult to do. Trying to maintain a program like that is very difficult to do. Oh, sorry, just a second here. I gotta close my door. All right. Okay, and so your giant program, sometimes called a kitchen sink program because it contains everything in one place, becomes extremely difficult to maintain. Right. So by partitioning a program, it creates a number of well-defined documented boundaries within the program. So it makes it easier, right? These boundaries or interfaces are invaluable in the comprehension of the program. So one of the things you need to remember that as a programmer, so in these introductory courses, it's very easy to get into the mindset that when you write a program, the only person that's going to read it is yourself, right? Or possibly your TA. But that's not the case in the real world, right? So when you make software in the real world, really, you're writing that software for other people to read, right? And so it is important, especially in an engineering context, that when you create your program, it's understandable, right, to other people who are reading your program. So you don't want to make this one giant class that's got everything in it and then have someone try to figure out how all of the different pieces in this one massive class are interacting, right? It's much easier if you give them small little pieces, right? And then you can, because it's easier to understand the small chunks of the program, and then you can see how all the small chunks interact with one another. Right. So how does Java do all this? Right. So how does Java provide the programmer with abilities to create an abstraction using encapsulation and modularity? So that's the topic of how we organize a Java program. So a typical Java program is just made up of one or more plain text files. I guess a more complicated Java program might have other different types of files, right? So if you have a program that's graphical in nature, then you might have a bunch of image files as well, right? If you're doing a some sort of three-dimensional game or something like that, you might have files that define the three-dimensional objects and so on and so forth, right? But the program itself is made up of just plain text files that you know are the Java files, right? So any file called .java. Right? Inside one of your Java source code files, the first line is either a 0 or one package name, right? So you are allowed to put your class, you're allowed to organize your classes into these things called packages. If your class needs to use another class, then it can import those classes, right? So that the program can use them. So typically that goes next. And then in a relatively simple typical program, what comes next is a single class. Right? So every .java file defines one class. That's not entirely true. Right? There can be more than one class here, but we'll see that later on in the course. So for now, every Java file has one class, defines one class. Right, so a.java defines the class A, b.java defines the class B, c.java defines the class C. Okay. Now, inside the class, there are one or more fields, or called or class variables. Okay, so a field, those are the variables that belong to the class or an object. Right? In other words, that's the information. Your fields are where the information of an object live, right, or are defined. Right. So these are just variables. So we'll see an example of that shortly. You then have these things called constructors. So constructors are the things that initialize the state of an object. So we've used the constructor, right? So every time you make an object, you write new followed by some constructor name, right? So how do the constructors work? Well, they're defined inside of the class. So every constructor that you can call, there is an implementation of those constructors inside your Java class file. Finally, there are the methods of the class. Right? So you know that, so we've used methods already. Where do the methods live, or where are they defined? Well, they're defined inside the class. So every method that you can call on an object, it has a definition that resides inside of the class. And then you can have multiple classes, right? So here's class 1, here's class 2, here's class 3, and so on and so on and so forth. Even the Hello World program uses at least 3 classes, and probably more, but it uses at least, oh, it actually uses much more than 3. Right? So the Hello World class needs the string class, it needs the object class, and it needs the system class. When you go to print out the Hello World, right? And actually, the system class needs a whole bunch of other classes as well. So even the simplest Hello World program ends up using several classes. Here's an example of a Java stack. So it doesn't matter if you know what the stack data structure is or not, right? This is how you could implement one in Java. And so this is just showing you an example of this picture here, right? So at the top, we've got a package declaration, right? Next, we have an import declaration, right? So this says that my stack class is going to use an array list. There's my package, there's my import. Next comes the class, right? Big box in blue is the implementation of the stack class. Right, now what's inside the stack class? There are some fields, there's a constructor, there are some methods. The fields, that's the information that's going to be stored. Those are the variables that the stack class uses in order to store the elements of the stack. Right, now notice I'm using a list to hold the elements of the stack. Right. The constructor initializes the state of an object. Right. So what do I have to do if I have a stack object that's got a list in it? Well, I need to make the list. Right. So the job of the constructors is to initialize all of the fields that are in the class, right, or that are in the object. Right. And then I have all of my methods here. Right. So there's a size method that tells me how many elements are in the stack. There's a push and a pop method to add an element to the stack and to remove an element from the stack. And then I've got a toString method that lets me print out a stack. in a nice, convenient way. Right. Again, it doesn't matter if you know what a stack is or not. Right. And it doesn't matter if you understand the implementation right now. Right. This is just an example. I think the notebook that talks about all of this tells you what a stack is, if you don't know what one is. Is the order of the fields, constructors, and methods important? No, the answer is no. In Java, you can put stuff anywhere you want. Which isn't true in C, right? So in C, so for example, in C, if I wanted to use this variable called stack, it has to be declared before you use it, right? In Java, you can take this line and stick it at the bottom if you want, and it'll work fine. But the normal structure of the class is to list the fields first, the constructors second, and the methods third. But the compiler actually doesn't care. Now, it's actually, so this is a organization of a typical simple Java program. It's actually, you can actually make a much more complicated program than this, right? So in other words, there's lots of features in the language that we don't talk about in this course, mostly because there's simply not enough time in the course. And this is true of any modern programming language, right? It's very difficult to get through all of the features of a modern programming language in a single course. You would need at least, I think you would need at least 2 to talk about everything in the Java language in a reasonable amount of time, right? And you wouldn't necessarily go into great depth either when you talk about these things, right? So there's a whole bunch of stuff that we don't really talk about in this course, although that's not, some of these we do, right? So classes inside classes, we'll see that later in the course. You can define a class inside of a method, which seems strange, but it turns out there's there are good reasons to do so. There are these things called anonymous classes, which is an unnamed class. Java 8 introduced these things called lambda expressions. We don't talk about those at all in the course. And then Java 9 introduced these things called modules, which we also don't talk about in the course. And then, we're up to version 17 of the language, so there's a whole bunch of other stuff that's not on this slide as well. But we try to hit all of the really important parts in this course. So, I mean, this slide is really here to indicate to you that even after completing this course, there's still a lot more to learn about the Java programming language. Okay, so what was the first line? Oh, package. So the first line of our class was this package declaration, right? Now, you don't have to do, you don't need to put your classes into packages if you don't want to. So if you have, if you're making a very, very simple program, then usually you don't put it into a package, right? But if you are, so this is especially true if you're writing a temporary Java program, right? So you're writing a program to figure out, to experiment with some feature of the language that you're trying to use somewhere else, right? Then there's no point in putting it in a package. The purpose of packages are to organize your classes. It's to give some sort of sensible organization of your classes. So a large program might consist of several thousand classes. And so usually when you create these classes, you want to organize them in some way, right? If you're thinking about this on a computer, then you want to put the classes into separate folders, right? Which might be the easiest way to think about packages, right? Packages are just folders. That's probably the easiest way to think about it, right? Folders are directories, however you want to, whatever you want to call them. Now the Java standard says that packages organize classes into these things called namespaces, right? So you define what's a namespace? Well, a namespace is just a container for names. Okay, so what does that mean, right? Well, I mean, again, the easiest way to think about it is just folders, right? So you can think of a package as being the label for a folder, right? You can put stuff into the folder, including other folders, right? Those other folders that you put into the folders, they have names as well, right? Those are the package names, and so on and so on and so forth, right? Now, what else can you put into a you can put other stuff into a folder, and so we'll describe that in a second. So packages are used to organize related classes and interfaces. So all of the Java classes, right? So everything that comes into standard library, they all go into a package called Java. Right? So all of the standard Java stuff goes into Java. I don't believe that that a programmer is allowed to put anything into this package either. I believe that's the case. So I believe that you're not allowed to put anything into the Java package. Now, packages are allowed to contain packages, right? So the Java package has packages called lang, util, and io, right? And all of the so the package lang contains all of the classes that are considered fundamental to the language. Right? Package util includes classes that are broadly very useful. Right? IO deals with input and output, right? So how you read and write data. So if you can put packages inside other packages, right? We need a way to describe the overall package name, right? So the fully qualified name of a package is the fully qualified name of the parent package, followed by a period, followed by the subpackage name. Okay, so what on earth does that mean? All right, so we know there's this package called lang. It's inside the package called Java. The fully qualified name of lang is java.lang. Package util, it's inside the Java package. The fully qualified name of util is just Java util. Inside a package, so what can you put? You can put other packages, or you can put classes and interfaces. So java.lang contains the classes object, string, math, and a few others. So these are all the classes that are considered fundamental to the language. Now, what's the fully qualified name of object? Well, it's just java.lang.object. Right? What's the fully qualified name of string? It's java.lang.string. Now, one of the reasons packages were introduced is to ensure that a fully qualified class name is unique, right? And so what that lets you do is that lets you or lets the compiler disambiguate classes with the same unqualified name. So, for example, the string class in Java is considered to be very important, which is why it's in java.lang. A lot of people complain about Java's string class because there are things you would like to do with strings that the Java string can't do. So it's not that uncommon for people to create or to find a different string implementation. Right? Now, the problem is you can't use, if you just use the name string, you can't use both classes in the same program because the compiler doesn't know which class you mean when you say string. Right? So when you say string, do you mean Java's string or do you mean your own custom string class? Right? And so the way you use both classes in the same program is that you use the fully qualified name of one or more of the classes. So for example, if you make your own string class in a package called your, right? And you can use both strings in the same program, right? And you use your string class, you use the fully qualified name of your class, right? Including when you call the constructor, right? When you use Java's string class, you just use the name string, right? I suppose you could, actually you can't do the alternative in this example, but you can choose, but if you're not using a class in java.lang, then you can choose which one you want you can choose which class you use with a fully qualified name. So that's the idea behind packages, right? So you can have many different classes, all have the same name, but you can still use them all in the same program. And this is not, this is something you can't do in C, right? So in C, it's one of the annoying things that in C is that you cannot use two types having the same name in the same, what does C call it again? The same compilation unit in C. So for example, if you make your own list type, and you also want to use someone else's list type, then they can't be in the same .c file. Right? There's no way to use them both in the same .c file. Whereas in Java, there is a mechanism where you can use two types with the same name. Okay, now the fully qualified names are supposed to be unique, but the language does not enforce this. So instead, there's what's called a package naming convention. So the idea is that when you create a package, or when you name a package, right, then that package should be organized using your domain name in reverse. For example, the domain name of the computing science department at Queen's is cs.queensu.ca. So if I were to create a a bunch of Java classes, and I wanted to hand them out to the rest of the world, then I would create a group of packages called CA. Inside that, I'd make a package called QueensU, and then inside that, I'd make a package .cs, and then I'd make my own packages here. Right? And domain names are unique. Right? So there's a central registry of domain names that guarantees that internet domain names are unique. And so that's the convention that's used to ensure Java packages are unique. But again, the language doesn't enforce it. So it's entirely possible that you find someone else's software that's in a package that might be the same as that might have the same name as another package. All right, so it's 20 after the hour, so I have to stop there. Any questions on today's lecture? Oh, wait, we do have a question. So assuming we have a name clash, unqualified names only compile correctly if they are from the standard Java. We have a name clash. We couldn't go Java lang string and then string. No, well, not in this example, because everything. So the way Java works is that everything in java.lang is automatically imported, right? So as soon as you say string, then Java assumes it's java.lang, not string, I believe. So I don't believe that in this particular example, you can have two string classes and use the Java class in the fully qualified way. Although I could check that, but I don't think you can, because again, because everything in java.lang is automatically imported. Right now, if you have java.util, so if you have a list class, right? So if you make your own list class, then you could use the list interface java.util.list in the fully qualified way. So you can import your list class, and this you write list. And then if you wanted to use the list interface, you could write java.util.list. Oh, well, the midterm, it's on queue. It's not proctored, Emily. So it's on queue during your lecture. Okay. Any other questions? All right. I will see you again on Wednesday, or if you have questions, I have office hours for this class tomorrow at 3:30. Okay, so thanks, everybody. See you when I see you.